Okay, so we are recording, and we're going to now, we've learned L'Hopital's rule from section 4.5, and it will be utilized for some problems in section 5.10. Section 5.10 deals with improper integrals. All right, so let me give you a moment to copy this problem down, and then we'll talk about it, okay? Let me see. Oh, Jingson's asking about the Tuesday's notes. You know, Jingson, how many pages were involved in those notes? I mean, of course, the recording's available for you to look at. Mario says it was like 11 pages. I think that's a safe estimate. Okay, so let's take a look at this integral here. This is called an improper integral, this integral. What is making the integral improper? Why are we calling this integral, the integral from negative infinity to 0 of x times e to the x dx, why are we calling that integral improper? What's different about that integral compared to integrals that you've had before? What's sort of strange about that integral?
They have an infinity value.
That's exactly right, Andrew. Very good. Very good. That's exactly right. This limit here is negative infinity. I mean, you're used to like if you had, let me ask you this, if you had this problem, x times e to the integral of x times e to the x dx, where the integral went from 1 to 4. Okay, that's a definite integral, right? You have definite limits on finite limits on the, well, you have finite limits on the top and the bottom here. And if you were to do that problem, by the way, what approach would you use? What integration technique would you use for this problem?
Integral by part?
Integration by parts, that's right. We would use integration by parts. So, and you would use integration by parts, and you would work the integral out. But for this improper integral, we have a negative infinity. And that means that the left-hand limit goes out to negative infinity. Okay, so first what we want to do is, I think we want to draw a picture. We want to draw a picture of our function. I mean, what are we trying to do here with this definite integral? Well, we have a function which is x times e to the x, and we're trying to find the area between this function and the x-axis from negative infinity to 0. So we want to find that area, but the question is the area finite? If the area is finite, we say the integral converges. But if the area is infinite, then we say the integral diverges. So converges means your area is finite. Diverges means that your area is either infinite or you can't determine the area. Naturally, if the integral converges, we want to evaluate what the finite area is. So let's go to the next page here and let's get a picture of this situation in our solution. So here is our picture. And if we were to graph this function in Desmos, the x times e to the x, where the limits go from the top limit is 0, and the right limit is 0. The left limit is negative infinity. So this curve, if it never touches the x-axis, this function. And what's happening is you're building up area. Okay, this is the area you're trying to find. That's what this definite integral means. You're trying to find this area, but there's always more and more area. Okay, as you go out to negative infinity, you can never reach negative infinity, right? So the curve keeps going, and you're always accumulating more and more area. The question is, how fast does this area accumulate? And does it accumulate at a rate fast enough so that the area converges? Okay, that's what you're trying to do here. So how do you do this kind of problem? How do you do this kind of problem? Well, all the integration techniques that you've learned so far involve finite limits. So what we have to do is we have to rewrite this improper integral as, well, I'm gonna replace the negative infinity with the variable t. I'm gonna replace the negative infinity with the variable t. Okay, so the integral now is the integral from t to 0 of x times e to the x dx. But what am I going to do with t? I'm going to let t go to negative infinity. So what I'm saying is this. Let me go to the whiteboard real quick, and I'll come right back. I'll come right back. I know you're copying. What I'm saying is this: is that this improper integral can be expressed as the limit as t approaches negative infinity of the integral from t to 0 of x times e to the x dx. Okay, that's so you see we're taking this improper integral and we're expressing it as the limit of a proper integral, because the proper integral has finite limit t on the bottom and finite limit 0 on top. But we're letting t go to negative infinity. And so this limit here, the limit of this finite integral, or the limit of this definite integral with finite limits, is equivalent to the improper integral. So you're always writing improper integrals as limits. And that's why limits were, it was important we talked about L'Hopital's rule. Okay, are there any questions on that before we get back to the solution? Okay, very good. Well, let me get back to the solution then. Hold on, that's the wrong thing. Wait. One moment. Let me go back here. One moment, class. Right. So here we are. Okay. So now we are here. My integral I always write my integral as an I. That was helpful, right, for some of those integration by parts problems, right? I write the integral as I, and now, all right, I have to evaluate. So the integral I is the limit as t approaches negative infinity of the integral from t to 0 of x times e to the x dx. Well, we know that this integral here, we have to use partial fractions. Now we're calling this a type 1 improper integral. Okay, there are two types of improper integrals. This is a type 1. A type 1 improper integral is an integral where one of your limits is either infinity or negative infinity. Okay, that's an type 1 improper integral. Well, we're going to use integration by parts on this. We're going to let u equals x and dv will equal e to the x dx. If u equals x, du equals dx, and v equals e to the x. And now I rewrite, so, integration by parts, the integral of u dv equals uv minus the integral of v du. That's integration by parts, right? So the limit of this integral then becomes the limit of my integration by parts integral. Are there any questions up to this step here?
Professor?
All right. Yes, Jing-sung.
Could you explain what the type I improper integral is again?
This is, I'm sorry, this is, we call this a type 1.
Oh,
This is a
it's a
Roman,
one.
Roman numeral.
Oh, okay.
No problem.
Okay, thank
Type
you.
1 improper integral is one where one of your limits was either infinity or negative infinity.
Okay, I'm guessing this was explained Tuesday.
I'm sorry?
I'm guessing this was part of the lesson on Tuesday.
Well, what we talked about on Tuesday was finding limits of functions. And you're going to see actually in this problem how L'Hopital's rule can be used to help you find a limit. See, we have to find this limit. Now, the first part here, there's no, that this is easy. You just substitute in 0 and t, and that gets you this expression here. The second part here, we have an integral from t to 0, and the antiderivative of e to the x is e to the x. So that's no big deal, right? This is just integration by parts. And so the expression inside the parentheses will be equal to negative t times e to the t minus the quantity e to the 0 minus e to the t. And notice I'm carrying the limit sign with me. I'm keeping that as we go because I've not taken the limit yet. The integral is going to be the limit of this expression as t approaches negative infinity. Okay. Are there any questions before we move to the next page?
Professor,
Yes, Andy.
is it possible to solve I with t and with the limit of t and I, and then name put 0 in it instead of put 0 already in the one?
We have to solve the integral as a limit problem.
Right. It's here they substitute 0 already in the first part of the integral. X exponential of x from 0 to t. Right. My question is it possible to just solve the integral with and then put 0 in t?
No. Oh, I see what you're saying. You're saying you mean just do integration by parts on the integral from t to 0 and then bringing the limit in later.
And we keep the limit, but we solve the whole. We solve the integral, and then we put 0 and t.
Oh, I
versus,
see what you mean. You mean do the indefinite integral
right?
and then put t in zero. Sure, that would be okay.
Okay.
That would be all right if you did the indefinite integral, figured out what, like basically if you did the indefinite integral, you would get. Want to be a little careful here. I tell you, it's more. You could do it, and then you put in your t and your 0 and t limits, and then you get down to here. You
Right.
could do it, but I think this is a little easier the way I'm doing it. But you could. It
Yeah.
would be acceptable.
Yeah. You get x minus you get x minus 1 factor of exponent of x, and then you put 0 and t in it to get to that.
Yeah, and so if you did that, then you would get this. You would
Exactly.
basically what you're
Right.
saying is you would get this expression here,
Right. The
only
first
it would
one.
have x's in it, and you would put the t in.
Right.
Yeah, that's okay. That's okay. And you know, so we're here. We're here. And now look at what we have. Look at what we have here in this limit. So is so -1 doesn't get affected by the limit, right? Because that's a constant. What would e to the t power go to? What's that going to go to as t approaches negative infinity? Okay, if you,
To 0.
that would go to 0. That's exactly right. Because if you had like if you have e to the negative infinity, that is 1 over e to the positive infinity, and that's just going to equal 0. So you have two terms that you know what's going to happen to them as t approaches negative infinity. But the first term, I have a negative here, but let me ignore that for the moment. The t times e to the t, what's that going to do as t approaches negative infinity? I mean, you have when you have t times e to the negative t, well, as t approaches negative infinity, okay, then t goes to negative infinity, and then e to the t approaches 0. So you have then the t times e to the t, okay, that's going to behave like, as t gets large, that's going to behave like the indeterminate form. I wish I could, let me just write this a little more nicely. The t times e to the t, as t goes to negative infinity, that's going to behave like the indeterminate form negative infinity times 0. And I don't know what that does. I don't know what that does. So what we're going to do is we're going to use the L'Hopital's rule. I'm going to write t times e to the t as t over e to the negative t. What I'm doing here is I'm taking t times e to the t, writing it over 1, and I'm multiplying by e to the negative t on the top and the bottom. Okay, that's really what I'm doing here. And so I get e to the negative t on the bottom, and then on the top, e to the t times e to the negative t. That's just equal to e to the t plus negative t, because you add the exponents. That's just e to the 0, which is 1. And so my expression here, my limit, can be written as the limit as t approaches negative infinity of t over e to the negative t. But now you have a function f right? You have a function f here over a function g. And the function f approaches negative infinity. T approaches negative infinity as t goes to negative infinity. And e to the negative t approaches positive infinity as t goes to negative infinity. Because if you have e to the negative infinity, that's just equal to e to the positive infinity, and that's infinity. So you have an indeterminate form that you can use L'Hopital's rule on. And that's what we do. We use L'Hopital's rule. We take the derivative of t, which is 1, and the derivative of e to the negative t, which is negative e to the negative t. And as t approaches negative infinity, this is just going to equal, it's going to equal 0. Okay, because e to the negative t goes to infinity. I mean, this whole expression here, if I write this out a little more, that's just going to be 1 over negative e to the negative infinity, right? And that just equals 1 over e to the infinity, and that would equal 0. So that means that in our limit above here, and you know, the negative doesn't affect that, that's going to go to 0, that term. And so now I know what everything's doing. Okay, and the only thing I have left as t goes to negative infinity is the negative 1. And so therefore, the integral, but by the way, what I do is the above here, that negative sign, I just pulled it out in front of the limit. And so the limit, let me just write it now here. And this is all in the recording. It's all in the recording. Hold on. So this limit here is just equal to the sum of these three limits. The limit of a sum is the sum of the limits. And I know what the second limit and the third limit is, and because I use L'Hopital's rule, I also know what the first limit is. I know all three of them. And so when I take the limit, I'm going to have 0 plus negative 1 plus 0, and so the integral equals negative 1. The integral equals negative 1. The improper integral equals negative 1. And so our integral converges. I'll show you, I have that written out on the next page, but please let me know if you have any questions. Okay. Well, so then, I'll go to the next page then, if we're good. All right, if everybody's good. Then to summarize, the integral equals negative 1. That integral, the area between the function x times e to the x and the x-axis, the area is finite and it equals negative 1. And incidentally, let me just go to the picture. That would make sense, right? Because all the area between the x-axis and that function x times e to the x, all the areas below the x-axis. How many learned in Calculus 1 that area below the x-axis is negative area? How many recall that from Calculus 1? Okay, Jinx and Ange and Javier remember that. And so, I mean, there's no way this area could be positive area, right? It has to be negative area. Very good. So then to summarize then, that area is equal to -1, and so the integral converges. The integral converges because our limit exists, and it's a finite number. Converge means to come together, right? To converge. But in math, it means the area is finite. Well, there's going to be a lot of converge used a lot of times in math to describe concepts. We're going to see it again when we deal with sequences and series. But for now, we're talking about integrals being converging. Okay, give you a moment to copy that down. Let me know if you have any questions. Very good, Sandia. Sandia is comfortable. Very good, very good. Okay, well, if there are no questions then, let's move to the next example. Okay, let me give you a moment to copy this example down. Okay, so now this integral is an improper integral also. Okay, but what's the problem? I mean, you know, there's no infinity or negative infinity in my limits. The two limits, 2 and 5, are finite limits. So why would this integral be improper, you think? What do you think the problem is?
The denominator could be 0 if x equal to.
That's exactly right, Ange. Very good. Look at your denominator. So in the denominator, like, well, here's our function. Here's our function, right? This is our function. So our function is 1 divided by the square root of x minus 2. Okay, write that a little nicer there. Hold on here. Okay, but x cannot, well, I mean, certainly x can't be, I'm going to say it's the right way. For that function, the domain of the function, because you have an x minus 2 in the denominator, you can't have the square root of 0, and you can't have the square root of a negative number. So like the domain would be from, hold on, it would be from 2 to infinity for that function f. But the point is, what we care about is that you can't have a 2. Okay, x is not allowed to be 2. And yet we have a 2 here as our bottom limit. Let me ask you this. This function at x equals 2, if we were to graph this function f of x, which is 1 divided by the square root of x minus 2, if we were to graph that, what would the graph look like at x equals 2? What would we see, you think? What kind of behavior would you see when x equals 2 for this function? Well, it's Sandhya, it's a fraction, and the function is a fraction. It's not defined at x equals 2. What do we tend to have with rational type functions where for x values where the denominator equals 0? What do we usually see in the graphs?
They tend to go to infinity.
That's right, and we call those what? What do we call those? It begins with an A. Well, asymptote. That's right, Joseph. That's right, Sandhya. So we would expect to see an asymptote for that function at x equals 2. Now let's go to the solution. And again, I draw a picture of my function. Okay, from 2 to 5. And indeed, at x equals 2, there is an asymptote, okay, for this function, 1 divided by the square root of x minus 2. Now the question is, I mean, here, this integral, here it is, it represents area under that function, area between the function 1 over the square root of x minus 2 and the x-axis. And we can, I can shade in this area. But now what's happening is you're getting area that's building up here. It's accruing, right? The function goes to infinity at that asymptote, and so you're accruing more and more area. The question is, how fast is the area accruing? Would it accrue fast enough, would it accrue at a fast enough rate so we could say the area is finite, or would the rate be too slow? And if it were too slow, the area would be infinite area. So again, what we have to do is we have to say, okay, well, let me write my improper integral as a limit. And I'm going to replace the 2, which is causing the problem. I'm going to replace that number with t. And I'm going to write the integral as the limit as t approaches 2 from the right side, because we're approaching 2 from the right here. Okay. The limit as t approaches 2 from the right of the integral from t to 5, that's what I'm going to be computing. And this is what's called a type 2 improper integral. Okay, it's a type 2. So we have a type 1 improper integral and a type 2 improper integral. Okay, and they're of course they're mentioned in section 5.10. under definition 1 in your textbook. But you know, these examples are reinforced. Well, actually, type 1 is mentioned. I mean, type 1 and type 2 are mentioned in the textbook. But these I don't want to deviate from the working out the problem here. I mean, it's pretty clear what we're doing here, and so now the question is, how are we going to solve this integral? So it's a substitution problem, right? We're going to let u equal x minus 2. Are there any questions so far?
Professor, isn't it when you go to 0 on the right side, when I limits of integral the from t minus 2 to 3 of
You're
1.
talking down here?
Yes.
Okay, so let's take a look at that. U equals x minus 2, so du equals dx. So
Yes.
just like a regular substitution problem, I'm converting my integral, which is with respect to x, to a new integral with respect to u.
Right.
So the 1 over square root of x minus 2 becomes 1 over square root of u, and
Right.
then dx becomes du.
Right.
But the limits now have to change.
Right.
How are we getting this 3? Well, 3, remember, u is equal to x minus 2. Top limit was 5. So 5 minus 3
equals
sorry, 5 minus 2.
2.
I'm hearing a little
3.
background. Hold on. 5 minus 2 is 3. And then, you know, when I have t, well, the u is x minus 2, so I get t minus 2 on the bottom. So that
Right.
gets us here. But go ahead now, Ange. Yes, go ahead.
So
Yep.
yeah, so the limit is the limit should be instead of 2 going to 2 in the right side, should be u going to 0 in the right side.
Oh, no, because very good question. When I integrate this integral, it's going to be a function of t because of the t minus 2. I'm going to be replacing my u variable with 3 and t minus 2, but I'm going to get a function of t. So,
oh, okay.
yeah, this doesn't affect what we're doing. We're going to let t approach 2 from the right. And yeah, so good question. Are there any questions now? Any other good questions before we continue the problem on the next page? Okay. Well, of course, we need the antiderivative of u to the negative 1/2 power. And I think you know what that is. That would be 2 times u to the 1/2 power. So now I'm taking the limit as t approaches 2 from the right, and I have to substitute in the 3 and the t minus 2 in my antiderivative, which I do here. And now what I do is I take the limit. So when I take the limit, I can be a little more descriptive here. I have a 0 there, but I could just have 2 minus 2, right? I'm going to substitute in 2 for t. And so this is going to get me 2 root 3 minus 2 times root 0. And I get 2 root 3. And that's what WebAssign would want on, for your next exam, your second exam, coming up on October the 7th. WebAssign would also want an exact answer. So, okay. Well, this is fine. We get 2 root 3. And so the integral converges. And that would make sense that the area would be positive area. Okay, let me just, I'll come back to this page. If we look at the picture, all the area here, I usually like to shade it in red. All of my area here is above the x-axis. So that area is all positive area. So I would expect my area to be positive, and it is. And so the integral converges. How many think this is pretty cool? Good. All right. Good, Angie. This is a convergent integral. Now, in WebAssign, when you work on this section 5.10, you have to be very careful because a lot of the problems are broken up into two parts. One part is, does the integral converge or diverge? And that's a multiple choice part, okay, where you got one try to get the answer right. And then the second part will be, put in like some numerical answer. But you have to be careful not to answer too quickly if the integral converges or diverges. You just have to be a little careful with that. Okay, are there any questions so far? Okay, let's look at another one before we go on our break here. One moment. Let me see. Let me bring up one more problem. If we're good with this, we'll move on. Hold on, class. Just give me a moment. No, you know what I think we'll do? Okay, I think we're good. Let's stop here. I'll stop the recording.